the next topic I am going to take up is matrix multiplication. First is matrix multiplication is a row column multiplication. Matrix multiplication is a row column multiplication. It is a row column multiplication. What do we exactly mean by this? I will explain it as we proceed with the lecture. Second thing is compatibility. As we studied in addition, that any two matrices cannot be added. Two matrices can be added only if they satisfy the compatibility condition. That is, they are of the same order. And similarly, any two matrices cannot be multiplied. Two matrices can be multiplied only if they satisfy the compatibility condition. Let A be M cross P and B be P cross N. Then these two matrices can be multiplied only if this is equal to this. That is, number of columns of A is equal to number of rows of B. That is, number of columns of pre-multiplier is equal to number of rows of the post-multiplier. Then only these two matrices can be multiplied. And the resultant will be of order M cross N. Their product will be of order M cross N. That is, C will be of order M cross N. So this is the compatibility condition, and resultant will be M cross N. Now we come to the rule. How we multiply two matrices? What is the method? The method is we multiply the rows of A with the columns of B. Rows of A with the columns of B. For example, we take the first row. First row will be multiplied with all the columns of B, and we will get first row, first column, first row with second column, and so on. First row with last column of B will be nth column. So first row nth column. Take the second row and multiply it with all the columns of B. Second row first column, second row second column, and second row last column is nth column, and so on. Last row of A will be, how many rows does A have? A has m rows. So mth row first column, mth row second column, mth row and nth column. So this matrix will be of order M cross N. And how exactly we carry out this multiplication? How do we multiply a row with a column? I am going to illustrate it now. For example, let A be equal to this and B be equal to this. Now, first is the multiplication possible? Do these matrices satisfy the compatibility condition? Now A is of order, how many rows does A have? 1, 2, 3. 3 rows and 2 columns. So this is a 3 cross 2 matrix. And B. Now B is how many rows? 1, 2 and 3 columns. So it is a 2 cross 3 matrix. Now these two are equal, therefore compatibility condition is satisfied. That is, these two matrices can be multiplied. And the result will be a 3 cross 3 matrix. This is equal to, it will be a 3 cross 3 matrix. Now what we do is we take the first row of this matrix and multiply it with all the columns. R1, C1, R1, C2, R1, C3. So what we do is we multiply R1 with this. How we multiply a row with a column? What we do is multiply first entry of this row with the first entry of this column. Multiply the second entry with second. first entry with first, second with second, and add the result. So this will be first entry with first. 1 into 1 plus second entry with second. 2 into 7. Now first row with the second. This will be 1 into 3, first entry with the first, second entry with second, plus 2 into minus 1. Now first row with the third column. 1 into 2, first entry with the first, second with the second, plus 2 into 1. Now all the columns have been multiplied. Now we take the row. Second row with the first column. Second row with first column. First entry with first, second with second. So this will be 3 into 1, 7 into 7. Now second row with second column. 3 into 3, 7 into minus 1. So this will be 3 into 3 plus 7 into minus 1. Second row with third column. 3 into 2, 7 into 1. So this will be 3 into 2 plus 7 into 1. Now we take the third row. Second row has been multiplied with first column, second column, third column. Now we multiply third row with first column, second column, third column. So first column, 2 into 1, 1 into 7. 2 into 1 plus 1 into 7. This into this. 2 into 3, first with first, second with second, plus 1 into minus 1. This into this. So 2 into 2, first entry with first, second with second, plus 1 into 1. And how much is this? 7 2s are 14 plus 1, 15. This is 3 minus 2, that is 1. 2 plus 2, 4. This is 49 plus 3, 52. This is 9 minus 7, so 2. This is 6 plus 7, 13. This is 2 plus 7, 9. 6 minus 1, 5. 4 plus 1, 5. So this is the result. This is how we multiply a row with a column. Note, this compatibility condition can be written in words as compatibility condition. Numbers of pre-multiplier is equal to number of post-multiplier. Number of columns of pre-multiplier is equal to number of rows of post-multiplier. This is the compatibility condition. Now we proceed on to take some questions. Now first is, let A be this much, B be this much, and C is this one. Verify that AB is equal to AC. Now B is not equal to C and A is not equal to 0. This is the first situation we are studying in which cancellation law is not true. That is, this A cannot be cancelled. If we cancel this A, we will get B equal to C, which is not true. B is not equal to C. So this can hold even if B is not equal to C. This matrix cannot be cancelled. So cancellation law is not true in matrices in general. It is true under certain conditions. Now A into B is equal to, now A is equal to this and B is equal to this much. We carry out the multiplication. This is 1, 2, 2 cross 3. This is a 2 cross 3 matrix. This has 1, 2, 3. 3 rows and 1, 2, 2 columns. So this is equal to this. Therefore, compatibility condition is satisfied and the result will be a 2 cross 2 matrix. So we multiply this row with this column, this row with this column. So first entry with first. This is 1 into 3, 3 plus 1 into 5 plus 5, 1 into minus 2. This is minus 2. Now first row with the second column. So 1 into 1, first entry with first 1 plus second entry 1 into 2, this is 2. Third entry with third, 1 into 4 is 4. And second row with all the columns. Second row with this column. So 3 into 3 is 9 plus 3 into 5 is 50. Plus 3 into minus 2 is minus 6. This into this. First entry with first, 3. Second entry with second, 6. Third entry with third, 12. This is a 2 cross 2 matrix. 2 cross 2 matrix. This is equal to 3 plus 5 is 8. 8 minus 2 is 6. This is 7. 15 minus 6 is 9. 9 plus 9 is 18. 12 plus 6 is 18 plus 3 is 21. So this is A into B. Now we find A into C. Now A is this much and C is this much. Now we see their orders. This is 2 cross 3 and this is 3 cross 2. 3 rows and 2 columns. So compatibility condition is satisfied and the result will be a 2 cross 2 matrix. So this into this. Multiply this row with this column. 1 into 4 is 4. 1 into minus 3 is minus 3. 1 into 5 is 5. This with this. 1 into 2. First entry with first. It is 1 into 2. Second entry with second. That is 5. Third entry with third is 0. Now this with this. First entry with first. 12. Second entry with second. Minus 9. Third entry with third. Plus 15. Now this with this. 3 into 2 is 6. 3 into 5 is 15. Third entry with third is 0. This is a 2 cross 2 matrix. And this is equal to, now this can be simplified into 9 minus 3, that is 6. This is 5 plus 2, 7. This is 12 minus 9 is 3, 3 plus 15 is 18. And 15 plus 6 is 21. Now let this be 1 and this be 2. So 1 and 2 imply A into B is equal to A into C. 6 is 6, 7 is 7, 18, 18, 21, 21. And B is not equal to C. B is not corresponding entries are not equal. Corresponding entries are not equal. Also, A is clearly not equal to 0 because all the entries are not 0. So we have proved A into B is equal to A into C. Now B is not equal to C and A is not equal to 0. So we have illustrated that the cancellation law is not true in general. Now next question is, we are given these 3 matrices and we have to find AB, BA. and verify is AB equal to BA. Now first we find AB. Now A is this much and B is this much. We have to multiply these two matrices. This is 3 cross 3, this is 3 cross 3. So compatibility condition is satisfied. And we carry out the multiplication. Now this row with this column. First entry with first, minus 2. Second entry with second, minus 3. Third entry with third, plus 6. Now multiply this row with this column. So this will be 3 into 1 is 3, second entry with second, 6, third entry with third is minus 9. Now this row with this column, 1 minus 1, this into minus 1, second entry with second, minus 3, third entry with third, plus 4. Now this row with this column, 2 into minus 2 is minus 4. Minus 1 into minus 1 is plus 1. Minus 1 into minus 6 is 6. This with this. First entry with first, 6. Second with the second, minus 2. Third with third, that is minus 9. Now this row with third column, 2 into minus 1. First entry with first, minus 2. Minus 1 into minus 1 is plus 1. And third entry with third, that is plus 4. Next is third row with all the columns. So third row with first column. So this will be 3 into minus 2. First entry with first, minus 6. Second with second, 0. Third with the third, that is plus 6. Now this with this. First entry with first is 9. Second with second is 0. And minus 1 into 9 is minus 9. So 9, 0, minus 9. 9 plus 0 minus 9. And this with this. Minus 3, 0 plus 4. Minus 3 plus 0 plus 4. This can be simplified into, now 6 minus 5, 1. 9 minus 9 is 0. 4 minus 4 is 0. 7 minus 4 is 3. 6 minus 11 is minus 5. Minus 2 plus 5 is 3. 6 minus 6 is 0. 9 minus 9 is 0. And 4 minus 3 is 1. So this is A, B. Now we find BA. BA. Now B is this much. And A is this much. We carry out the multiplication. Now first row with first. This will be minus 2 plus 6 minus 3. Minus 2 plus 6 minus 3. Minus 2 plus 6 minus 3. This into this. Minus 6 minus 3, 0. Minus 6 minus 3 and 0. This is minus 6 minus 3, 0. This into this. This will be 2 minus 3 plus 1. Now next is this into all the columns. This into first column. Minus 1 into 1 is minus 1 plus 4 minus 3. Minus 1 plus 4 minus 3. This into this. Minus 3, minus 2 and 0. Minus 3, minus 2 and 0. This into this. This is 1 minus 2 plus 1. 1 minus 2 plus 1. This into this. This is minus 6 plus 18 minus 12. Minus 6 plus 18 minus 12. This into this. Minus 18 plus minus 9 and 0. This into this. This is 6 minus 9 plus 4. 6 minus 9 plus 4. And this is equal to, now simplify this. This will be 6 minus 5 is 1. Minus 9. And this is 3 minus 3 is 0. This is minus 4 plus 4, 0. Minus 5. 2 minus 2 is 0. And minus 18 plus 18 is 0. This is minus 18 minus 9 is minus 27. And this is 10 minus 9, 1. Now let this be 1 and this be 2. 1 and 2 imply A into B is not equal to B into A. You can compare the two matrices. 1 is equal to 1, alright. 0 is minus 9. No, these are not equal. This may be equal. This is 3 is not equal to 0. So, these two matrices are not equal. So, the second important thing we now have studied is commutative law is not true. A into B is not equal to B into A. Order of multiplication cannot be interchanged. Now next part is we have to prove AB plus AC is B plus C. You can see the statement on the side sheet. So AB from first equation is 1 0 0 3 minus 5 3 0 0 1, and AC we will have to find. A is this much and C is this much. You can see the statement on the side sheet. This is equal to, now multiply this row with this column. So first entry with first, 3 plus 15 minus minus plus 2. 3 plus 15 plus 2. 3 plus 15 plus 2. This into this. 1 plus 6 minus 4. 1 plus 6 minus 4. Now all the columns have been multiplied. Now this with this. So this will be 6 minus 5 plus 2. 6 minus 5 plus this into this. 2 minus 2 minus 4. 2 minus 2 minus 4. Now this with all the columns. This with the first column. 9 plus 0 plus 2. 9 plus 0 plus 2. This with this. 3 plus 0 minus 4. 3 plus 0 minus 4. This is a 3 cross 2 matrix. The order of this is 3 cross 3. Order of this is 3 cross 2. So the compatibility condition is satisfied and the result will be a 3 cross 2 matrix. And this is equal to, now this is 18 plus 2, 20. This is 7 minus 4 is 3. 8 minus 5 is 3. 2 minus 2 is 0 minus 4. This is 11. And this is minus 1. This is a 3 cross 2 matrix. Let now this be 3 and this be 4. From 3 and 4, what we realize is AB and AC are not compatible for addition. Therefore, left hand side doesn't exist. Therefore, left hand side doesn't exist. And similarly, on right hand side, B and C are not compatible for addition because B is of order 3 cross 3 and C is of order 3 cross 2. Therefore, these two cannot be added because compatibility for addition is matrices must be of the same order. This is 3 cross 3, this is 3 cross 2. Therefore, they cannot be added. Therefore, RHS also does not exist. We can also deal with this question as now A into B is equal to A is 3 cross 3 and B is 3 cross 3. Therefore, AB is of order 3 cross 3 and AC. A is of order 3 cross 3 and C is of order 3 cross 2. Therefore, AC is of order. Now this is the compatibility condition. The result will be 3 cross 2. Here this is the compatibility condition. Result will be 3 cross 3. So this is 3 cross 3 and this is 3 cross 2. Therefore, AB and AC are not compatible for addition. Therefore, left hand side doesn't exist. Therefore, left hand side doesn't exist. On RHS, order of B is 3 cross 3 and order of C is 3 cross 2. Therefore, B plus C is not possible because B and C are not compatible for addition. Therefore, RHS also doesn't exist. Therefore, both left hand side and right hand side does not exist. Therefore, AB plus A not equal to A into B plus C. But here, if both the left hand side and right hand side exist, then left distributive law as well as right distributive law will be true, as we will see in the next part. If both left hand side and right hand side exist, then distributive law will be true. Now third part is A plus B into C equal to AC plus BC? Is the right distributive law true? Now A plus B is equal to, now A is this much and B is this much. You can see the side sheet. Now this is equal to addition of these two matrices. Add the corresponding entries. 1 minus 2 is minus 1. 3 plus 3 is 6. Minus 1 is minus 2. 2 minus 1 is 1. Now empty at 2 place, empty at 2 place. So this is minus 1 plus 2. Minus 1 minus 1. Entries at the same place will be added. This is minus 2. 3 minus 6 minus 3. This plus this 9. This plus this minus 5. This is A plus B. Now A plus B into C. This is equal to, from 5 A plus B is this much and C is given to be this much. Now we carry out the multiplication. So this into this, minus 3 plus 30 plus 4. Minus 3 plus 30 plus 4. This into this, minus 1 plus 12 minus 8. Minus 1 plus 12 minus 8. This into this, 3 plus 5 plus 4. 3 plus 5 plus 4. This into this, 1 plus 2 minus 8. 1 plus 2 minus 8. This into this, minus 9 plus 45 minus plus 10. So this is minus 9 plus 45 plus 10. This into this, minus 3 plus 18 minus 20. So this is minus 3 plus 18 minus 20. This is a 3 cross 2 matrix. This is 3 cross 3. This is 3 cross 2. Compatibility is satisfied and result is 3 cross 2. This is equal to, now 34 minus 3. This is 31. Minus 9 plus 12 is 3. 9 plus 3 is 12. 3 minus 8 is minus 5. 10 minus 9 is 1 plus 45 is 46. This is minus 21 plus 18. This is minus 5. Minus 23 plus 18 minus 5. Now we find AC. Now AC is equal to, now we have already found AC. AC is equal to this much from fourth equation. And next thing we require is B into C. Now B is this much and C is given to be this much. We multiply these two matrices. This into this. This will be minus 6 plus 15 plus 2. Minus 6 plus 15 plus 2. This into this. This is minus 2 plus 6 minus 4. Minus 2 plus 6 minus 4. This into this. This is minus 3 plus 10 plus 2. Minus 3 plus 10 plus 2. This into this. Minus 1 plus 4 minus 4. Minus 1 plus 4 minus 4. This into this. Minus 18 plus 45 minus plus 8. This is minus 18 plus 45 plus 8. This minus 6 plus 18 minus 16. So minus 6 plus 18 minus 16. This is equal to, now This is 17 minus 6. 17 minus 6 is 11. And 6 minus 6 is 0. This is minus 1 plus 10 is 9. 4 minus 4 is 0. Minus 1. Now 18 minus 18 plus 8 is minus 10. Minus 10 plus 45 is 35. And this is 18 minus 16 is 2. Minus 6 plus 2 is minus 4. Now we find AC plus BC. AC plus BC is equal to, how much is AC? AC is 23, 3, minus 4, 11, minus 1. This is AC. And BC is this much. Plus 11, 0, 9, minus 1, 35, minus 4. And when we add these two matrices, we get, add the corresponding entries. This will be 31. This plus this is 3. This plus this is 12. This plus this is minus 5. This plus this is 46. This plus this is minus 5. Say this has 6 and this has 7. 6 and 7 imply to C is equal to AC plus BC. Compare these two. Compare these. 31 is equal to 31. 3 equal to 3. This is equal to this. This is equal to this. These two are equal. These two are equal. So the corresponding entries are equal. Therefore, these two matrices are equal. Therefore, right distributive law is true here, but left distributive law is not true. We now take up some properties on matrix addition and multiplication. So we have already taken these properties in some examples, and we have derived a bit of understanding. I will make a table of these properties here for future consultation. So first of all, I take up addition of matrices. The property is commutativity. Now, let A be any two matrices of the same order, then A plus B is equal to B plus A. Commutativity is true. A is additive to B or B is additive to A does not matter. Order of the matrices does not matter. I am not writing the compatibility conditions here. I made a general note. Preconditions are satisfied wherever required. For multiplication, this property is not true. AB is not equal to B into A. And while doing examples on multiplication, I told you that we have studied this is the first situation where A into B is not equal to B into A. In real numbers, 2 into 3 used to be equal to 3 into 2. Multiplication was always commutative. Addition was also commutative. But here, matrix multiplication is not commutative. Next property is associativity. Associativity of addition. A plus B plus C is equal to A plus B plus C. That is, bracket can be moved from B plus C to A plus B. That is, we can first find addition of B and C and then add this addition to A plus B plus C. And here we find A plus B and then add it to C. both the results will be same. Next is associativity of multiplication. Matrix multiplication. A, B, C is equal to A, B, C. Now, if we put these two in one bracket and these two in one bracket, the result will be C. That is, if you first find multiplication of B with C and then pre-multiply it with A. And if you find AB and post-multiply it with C, the result will be C. But the order of the matrices cannot be changed. If you find BC, it should not be CB. Because commutativity is not true. Order of the matrices cannot be changed. If it is ABC, it should be ABC. Brackets can be changed. You first find this and multiply with this, or you first find this and multiply with this. This can be done, but order of the matrices cannot be changed. You must be very, very cautious while dealing with matrix multiplication. Commutativity is not true. Next is identity. Before taking up these two properties, identity and inverse, I would like to make the general concept of identity and inverse clear. First of all, I explain it for real numbers, and then I will take it for matrices. Let us consider a real number, say 2. Now, what is identity? Additive identity or multiplicative identity. Identity also depends upon the operation. If it is addition, identity will be different. If it is multiplication, identity will be different. So the definition of identity is what should be added to 2 which leaves it unchanged. That is the identity. What can be added to 2 which leaves it unchanged? What can be multiplied with 2 which leaves it unchanged? That is, it leaves it as 2. This is identity. So what is that number which can be added to 2 and leaves it as 2? It is 0. What is that number which when multiplied with 2 leaves it as 2? It is 1. So additive identity is 0 and multiplicative identity is 1. Now I come to the concept of inverse. What is the general concept of inverse? This is the number 2. Say operation is addition. And here say operation is multiplication. And the general concept is what when added to 2 gives us the identity. Additive identity is 0. What when multiplied with 2 gives us the identity. Multiplication is the process, so we will take multiplicative identity. Addition is the process, so we will take additive identity. So what is that number which when added to 2 will give us the additive identity? What is that number? That number is minus 2. What is that number which multiplied with 2 gives us 1? What is that number? That number is 2 to the power of minus 1. So minus 2 is the additive inverse of 2 and 2 to the power of minus 1 is the multiplicative inverse of 2. Now I come to the matrices. Let A be n cross n matrix, then there exists a null matrix O of order n cross n such that A plus O is equal to A plus O is equal to A. It leaves it unchanged. That is the identity. Identity is the matrix which when added to A unchanged. Now, this is equal to, it can be added from right as well as from left. The result should remain unchanged. Then O is the identity. I have already explained you identity and inverse. Let A and N be any n cross n matrix, then there exists an identity matrix of order m and identity matrix of order n, such that A n cross n into I n is A n cross n. I n is n cross n. So compatibility condition is satisfied and we will get the result as m cross n matrix. And if we pre-multiply it with identity matrix, what we get is I n into A m cross n. So here I is m cross n and A is m cross n, so compatibility condition is satisfied and the result is again m cross n. So for post multiplication of A with I, we must have I as I n. And for pre-multiplication, we must have I n. There is a difference. So you must note this down. So this is the identity. Left identity and right identity can be different. If A is a square matrix, then both of these identities will be same. Now next property is inverse. If addition is the operation, then let A n cross n be equal to Aij n cross n, then there exists a matrix minus A n cross n equal to minus of Aij n cross n, such that A plus minus A is 0. 0 in matrices is the null matrix. Each and every entry is 0. Is equal to minus A plus A. Minus A plus A, if you add additive inverse from right or you add additive inverse from left, the result is null matrix. So this is the inverse. Then additive inverse of A is minus A. Next is multiplicative inverse. Multiplicative inverse of a matrix. Let A be a square matrix, then multiplicative inverse exists only for square matrices. Then if there exists a square matrix B such that, what is the definition of inverse? A matrix which when multiplied with A gives us identity. Multiplicative inverse of 2 was 2 to the power of minus 1. 2 into 2 to the power of minus 1 is identity 1 of numbers. Here the identity must be that of matrices. So there must exist a square matrix B such that A into B is identity. And this must be equal to B into A. B is inverse of A. Generally B is denoted by A inverse. Will be taken up in a topic determinants. We will deal with the details only in chapter of determinants. Next is cancellation laws. Cancellation laws for addition. A plus B is equal to A plus C. Then you can cancel A from both sides and you will get B equal to C. So cancellation laws hold for matrix addition, but they do not hold for matrix multiplication. A into B is equal to A into C. Then you cannot cancel A from both sides and get B equal to C. No. This can only be done under certain condition. In general, you cannot cancel A on both sides and get the result B equal to C. So cancellation laws do not hold in general for matrix multiplication. Can be cancelled only if determinant of A is not equal to 0. This we will discuss in the next chapter. There is chapter on determinant. And sixth property is A n cross n into null matrix is null matrix. Or OPM into AM cross n, if we multiply A from right with the null matrix, or we multiply A to the left with the null matrix, the result is same. That is, we get the null matrix. Here the order of the null matrix will be M cross P, here it will be P cross N. Note, A into B equal to 0 does not imply either A is 0 or B is 0. As we used to do in numbers. You used to make factors, and then you say that product of two factors will be equal to 0 if either first is 0 or second is 0. But this cannot be included in matrices. A into B equal to 0 does not imply either A is 0 or B is 0. They can be both non-zero and still the product can be 0. So these properties you must always keep in mind. The last property I am going to take up is distributivity. The two distributive laws, left distributive law and right distributive law. A into B plus C is AB into AC, and A plus B into C is AC plus BC, and these two laws hold only when both these sides exist. That is, the matrices involved are compatible. With this, I end up this discussion on properties of matrices. Now next question is, if A is equal to this much, show that A is the root of this much. Use this to find A4. Now we are given fx is this much. Therefore fa. Now we have to show that this is a root of this equation. So we find f of A. F of A will be A square minus 5 A plus 7. But this equation is not compatible. Why? Because this is a matrix. 5A will be a 2 cross 2 matrix, and this matrix cannot be added to 7. 7 is a scalar. For numbers, the identity is 1. But for matrices, the identity is I. So we must write 7 into I. Only then this expression will be defined. So for matrices, you must write 7 into I. This is very important. Now what we do is we find A square. A square. This is equal to 3, 1, minus 1, 2 into 3, 1, minus 1, 2. And this is equal to this into this. 3 into 3 is 9. 1 into minus 1 is minus 1. 9 minus 1. This into this. 3 plus 2. That is 5. This into this. Minus 3 minus 2. Minus 5. This into this. This is minus 1 plus 4. Minus 1 plus 4. This is equal to, this is 8, this is 5, this is minus 5 and 3. And minus 5a. Minus 5a will be equal to Multiply each and every entry of A by minus. So this will be minus 15, minus 5, and this will be plus 5 and minus 10. Plus 5 and minus 10. Multiply each and every entry of this by minus 5. Minus 15, minus 5, plus 5 and minus 10. And 7i. 7i is equal to 7 into I. I is 1, 0, 0, 1. For 2 cross 2 matrices, identity is this much. So this is equal to 7, 0, 0, 7. And therefore, A square minus 5A plus 7I is equal to A square. A square is 8, 5 minus 5, 3 plus minus 5 is minus 15 minus 5, 5 and minus 10 plus 7i. 7i is 7, 0, 0, 7. And this is equal to, now 8 minus 15 is minus 7. Minus 7 plus 7 is 0. So this is 0. 5 minus 5 is 0. 0 plus 0 is 0. Minus 5 plus 5 is 0. Plus 0 is 0. Add all the 3 entries at this place. 3 minus 10, 7. So this is 10 minus 10 is 0. Therefore, A is a root of fx is equal to x square minus 5x plus 7. Now 1 implies A square is equal to 5A minus 7I. Therefore, A4 is equal to A square into A square. That is 5A minus 7I into 5A minus 7I. And this is equal to this into this. You must keep in mind that matrix multiplication is not commutative. So you must keep the order of the two matrices same. If it is getting multiplied from left, you must keep it on the left. So this will be 25A square. This into this. This will be minus 35A into I. Minus 7 into 5 is minus 35 I into A. This into this. Plus 49 I into I. This is equal to 25 into A square. How much is A square? A square is 5A minus 7I. This is 5A minus 7I. Minus, this will be 35A into I is A. Minus I into A is again A. 35A plus I into I is I. 49 I. We have used the following results. A into I is A is equal to I into, and I into I is equal to I. This is equal to 125A minus 7 into 25. This is 175I minus 70A plus 49I. This is equal to Now 125 minus 70 is 55A minus, now 175 minus 49. 175 minus 49 is minus 126I. And this is equal to 55A. How much is A? A is 3, 1 minus 1, 2. 3, 1 minus 1, 2. Minus 126 into I. I is 1001. So this is equal to 55 into 3, 165. This is 55. This is minus 55. And this is 110. Plus minus 126, 0, minus 126. And this is equal to, how much is 165 minus 126? 39. This is 55. This is minus 55. And 126 minus 110 is 16. So this will be minus 16. So A to the power of 4 is this much. You can also directly find A4. Multiply A square with A square and get the result. And you will see that these two results are equal. But here in the question, we have to use this equation to find A4. So we have done it like this. But A square can be multiplied with A square and you can verify that these two are equal. Now next is, under what conditions is the matrix equation this true? Now A plus B into A minus B is equal to A square minus B square if and only if, open this bracket, this will be A into A minus A into B. Matrix multiplication is not commutative. Therefore, if you are multiplying this with A from left, it must be kept on left side. This is B is on the left. So in this term, we must write B into A. This into this minus B into B. This is equal to this. If and only if this is A square minus A into B plus B into A minus B square is equal to A square minus B square. If and only if, now A square cancels with A square and minus B square cancels with this. If and only if minus AB plus BA is equal to 0. If and only if AB is equal to BA. If and only if A and B are commutative for multiplication. And only if commutative law holds good for multiplication of A and B. Only then this formula will be true. But it is not true in general. Now next question is, if A and B are square matrices of the same order, explain why in general A plus B whole square is not equal to A square plus 2AB plus B square. This is not equal to this. This is not equal to this. I am taking up the first part. A plus B whole square is equal to A plus B into A plus B, and this is equal to A into A plus B, A into this plus B into A plus B. This is equal to A into A plus A into B plus B into A plus B into B. We are multiplying this with B from left, so it must be kept on left. Here we are multiplying B from left with A, therefore A must be on left. So this is equal to A square plus A into B plus B into A plus B square, and which is not equal to this. Therefore A plus B whole square is not equal to A square plus 2AB plus B square, because A into B plus B into A is not equal to 2AB, because matrix multiplication is not commutative. Matrix multiplication is not commutative. Similarly, you can try the other parts yourself. Try yourself. You can try the other parts yourself. Now next is, if A and B are square matrices of order n, then prove that A and B will commute if and only if A minus lambda I and B minus lambda I commute for every scalar lambda. Now A minus lambda I and B minus lambda I commute if and only if A minus lambda I into B minus lambda I is equal to B minus lambda I into A minus lambda I. If and only if A into B minus lambda I minus lambda I into B minus lambda I. A into this minus lambda I into this must be equal to B into this, that is A minus lambda I minus lambda I, A minus lambda I, and this is equal to AB minus lambda AI minus lambda into IB minus minus plus lambda square I into I. This is equal to B into A minus lambda into BI minus lambda IA into minus minus plus lambda square I into I. And this can be written as AB minus AI is A minus lambda IB is B. Lambda square I into I is I. B into A is B minus lambda BI. BI is B. I is A. And this is I. If and only if now AB, now this lambda A cancels with this, lambda B cancels with lambda B, and lambda square I cancels with lambda square I. So we are left with AB is equal to BA. If and only if A and B are commutative. If and only if A and B are commutative. Hence,